So let's come back to our last talk for today. And so our speaker is Professor Suresh Nayak, and he's going to talk about trace maps and residues in Grothendieck duality.
Thanks. So this will be the part 3 of my lecture series, and this is on Grothendieck duality. I briefly talked about it in the first lecture, and then later on we went into Verdier duality, for which I gave a sketch proof last time. So let me just recall and also reset some or introduce some notation. So C will be the category of finite type separated maps. Of Noetherian schemes. And I will introduce one more notation. So for X in C, not so much notation, but a fact. No, there is no field. Yeah, okay, sorry, yeah, I forgot to mention. So I assume some background in algebraic geometry. Noetherian schemes are things which locally are given by spectrum of prime spectrum of the Noetherian ring. So it's a ringed space over which is covered by finitely many affine opens, and each one of those affine opens is spectrum of a Noetherian ring. And finite type maps means at the level of Noetherian rings, it's a map finite type. And separated is a sort of a Hausdorff kind of condition. So one says that the diagonal has a closed image. If the diagonal of the map has a closed image, then it's called separated. So we'll just, this is just a technical condition to ensure some things don't go wrong. And for X in C, we have an equivalence. So this is the derived category of quasi-coherent sheaves on X. Meaning it's the objects are schemes and the morphisms are the maps. That's the way we usually write it. So when we say X is in C, it means it's a Noetherian scheme. So for a Noetherian scheme, we have an equivalence of categories. And this is quasi-coherent homology. So again, this is the derived category. This is the derived category of chain complexes whose individual elements are quasi-coherent modules on X. And this is the derived category of all possible OX modules, not necessarily quasi-coherent, but whose homology is quasi-coherent. And let me remind you, quasi-coherent means that locally, if your scheme is given by a spectrum of a ring, then it's given by a module associated to that ring. And it behaves well with respect to localization. So the module associated to a certain affine open set, if I give you a module associated to a certain affine open set, then for the localized open set A, let's say the ring is A, then the localized open set spec spec AF, where F is inverted, you'll give the module M localized at F. So for spec A, which is an open subset, we'll give the module M. Then for the open subset spec AF, we'll give the module MF. Of course, this is not at all a complete definition, and a better way to say it is it's locally given by finite presentations since it's Noetherian. But Okay, we will not, I will not write down the formal definition. So here, this is potentially a larger category, because here we allow all possible complexes, complexes of all possible modules, but only the homology is required to be quasi-coherent. Here we are looking at complexes whose modules are quasi-coherent. So of course the homology will be quasi-coherent. And the claim is that if you look at the natural map, sending any complex to itself, this is actually a equivalence of categories. So this has been proved in different places. So we'll just assume this fact. So based on what I said in my first lecture, so we are looking for a localizable functor or rather a family of functors. We're looking for localizable functors over C with values in DQC. I'll briefly explain what this means. And in fact, instead of DQ, oh, sorry, I forgot to mention. So instead of writing DQCOH co, I will also write it as DQC. So that's a little shorter. So that's just renaming it. So I'll just put DQC, quasi-coherent. And so we'll take values in DQC here. So I'll briefly say what it means. And in fact, I should mention, or perhaps DQC plus. So DQC plus means complexes which go in the rightward direction under homology indices. So the maps are going this way. So which means that the homologies all vanish in negative degrees. Negative degrees here, negative is counted on the left side. And so what this means is that means that basically you'll have, if I have x to y, f, then I'm looking for an f shriek which will go from DQC y to DQC x. So this is the kind of thing I'm interested in. So this is what I mean by a family of functors, but it should be localizable. So I'll very briefly mention what is that. But before that, such that I want some interesting things to hold, some useful properties to hold, such that, so number one is G composed with F shriek is naturally isomorphic to F shriek G shriek for, let's say I have X to Y to Z. I have maps like this, then under compositions, this should behave well. So of course, this is actually, if you think about it, this itself is not good enough because so there's an obvious property for triple intersections. So it should be compatible with triple compositions, sorry, property for triple compositions. So I have three maps, and then you will see that this isomorphism should have some sort of associativity property. So that's number one, and number two is if F is proper, then that implies F shriek should be a right adjoint. So F shriek is equal to F cross. So unfortunately, I'm introducing a lot of notation here. So this is again something I had mentioned last time, and so cross is the right adjoint to RF lower star. So RF lower star will go from dx to dy, and we'll put QC here. So F cross by definition will be the right adjoint, but I don't want F shriek to be F cross all the time. So I don't want the right adjoint all the time. And that's because as I said the first time in my first lecture, the right adjoint is not really a localizable functor. If you take an open set, then the right adjoint, or an open immersion, then the right adjoint is not restriction. And so if you take the right adjoint and restrict to an open set, that is not the right adjoint of the composite map. So that's not really the good thing to have. So here I should just very briefly mention that if you have two maps, then let's say F and G like this, then G lower star, F lower star is GF lower star. And because of this, we see that the lower star behaves well under compositions, and therefore that implies that F cross G cross is canonically isomorphic to GF cross. So we have good behavior if we are sticking to right adjoints, though we will not do that. But when both the maps are proper, that's a good thing. And the third thing is F is smooth of relative dimension n. And that implies F shriek should look like F upper star twisted by or tensored by omega n F shifted by n. Again, this is something similar to what happened in the duality, where we twisted it by the orientation sheaf. And here we will shift it by module of differentials, nth module of n differentials. So in fact, let me mention that actually 3. So in fact 3 already implies 3 and 1 imply F shriek is localizable. And so this is just a reminder that open immersions are smooth of relative dimension 0. So because an open immersion smooth of relative dimension 0. And in this case, if you look at, so then n is 0, and so this will just be nothing, just O, and this will just be F upper star. So in this case, F shriek will be isomorphic to F upper star, and that is the like restriction. So in some sense, I don't really have to insist that we are looking for a localizable functor. If I have 1, 2, 3, then I'll automatically get it. But the other interesting fact is that we can also get something explicit from these requirements if F is a closed immersion. So if for a closed immersion, if I take a closed subset given by some ideal, then given by coherent ideal I inside OX, then in this case, by Hom tensor adjointness, I can say what the right adjoint should look like. Then by Hom tensor adjointness, one sees that cross, or rather, I should just say that, sorry, there's no F, there's I. Okay, so one sees that R Hom dot OX gives a right adjoint. to RF lowest, RI lowest. So then I can just say that the functor that I'm looking for, at least, this actually lives on X, so you have to restrict yourself to Z. This lives on X, but in fact, it has homology supported in Z. So these are nothing but sections supported on Z. That's what it means. Look at derived sections supported on Z. And so you can represent it by a complex of OZ modules. And I mean, you can, so actually maybe the technical, yeah, it's just inverse image functor, but you can just pretend that you are just restricted to Z. So this will give you a right-hand joint. So ring theoretically, it's all we are saying is that if I have A maps to A mod I, then R hom A mod I into a module is nothing but right adjoint to the restriction functor which restricts any AI module to think of it as A module. So this is just Hom tensor adjointness. One final remark is if we go back to Verdier duality, one could ask, I mean, one is saying there's a right adjoint only when F is proper, but otherwise one is not looking for the right adjoint. So one could really ask, is there a direct image with proper support? Functor. So that we have a right adjoint F upper streak just as in Verdier duality directly. So why can't we have a, so that we have right adjoint to RF lower streak? So can we just create F upper streak by simply just having some functor F lower streak with proper support, direct image with proper support? So don't just take RF lower star, don't take F lower star, but maybe look at some subset of sections which have proper support over the base. So you can in fact try to define such a functor, but the main problem is that such a functor will not take quasi-coherent sheaves to quasi-coherent sheaves. So I won't go into this, but I'll just say that can define, but does not preserve quasi-coherence. Even for an open immersion, you can check this, does not preserve quasi-coherence. So we are forced to therefore put these conditions and not, I don't see how to simplify it further. So just to summarize the picture, this is a meaningless picture, but okay. So think of this as proper maps, and think of this as smooth maps, and then think of these as, okay, I guess I'm not supposed to write up there. So think of these as closed immersions. And think of these as open immersions. So I'm looking for a functor which looks like cross here, and here I'm looking, okay, I didn't give a name to this functor. Where did it go? This one. So let's give this a name, but I'm reluctant to introduce one more symbol because then anyway, these symbols don't really have any particular meaning. So let's just call it FSM, SM standing for smooth. So for a smooth map, we will try to use this functor. It's again, you can see it's well behaved under composition of smooth maps because the omega n's, they get multiplied accordingly. So I have a functor, family of functors here, family of functors here. On this set, I mean, it's just restriction, I know, and this one here on this set is closed, is given by some explicit formula. The question is, can we somehow put everything together? So So the way we'll do it is there are two approaches to Grothendieck duality in literature. The first one is, so I'll very briefly go over both of them. We'll call the constructive approach. And then the second one is abstract, or let's say more general. So this one was the original way of defining this family of functors F shriek, but it has some complications in it. This is a more abstract one, which was initiated by Deline and Verdier, and we'll slowly get towards the second one. But there are some interesting features in the first one which also need to be mentioned. So very briefly, the first one, basically you factor any fx to y in C as, so let's say then this is I and H, and we'll call this as closed immersion, and this is smooth. This is not the only way of factoring, but these kind of factorizations are available quite often. And then set F shriek to be equal to I cross and H smooth. So for smooth maps, I know what I'm looking for. For closed immersions, I know what I'm looking for. So therefore, just put them together. And the other one is just the other way. So factor any as again x, but now I'll call it x bar and y. Let's call this as I, and this I will call it as f bar. Here this is open immersion, and this is proper. So here we are trying to embed X as a closed subset of something smooth. So maybe affine space or projective space. So we are trying to imagine X as a quasi-projective, relative quasi-projective object over Y. Here we are sort of trying to compactify the map. I mean, this should be thought of as compactified, and this is the open set of that. And then here, of course, and set. Again, we know what to do over each open set. For each particular term of the factorization. So just set F shriek is equal to whatever you want for this one and this one. What is it? So F bar cross and I star. I star being just restriction. So look at the right adjoint and restrict it. So that is the other approach. Okay, so I have two approaches. And so some common issues will arise in both the approaches. So let me mention those. So first is, so this is A, both for 1 and 2. We must prove that F shriek is independent of the choice of factorization. Second, we must prove that something like this third, and that is actually the most crucial question. Why does there exist such a factorization? And the fourth one is that even if you do all this, then you still have to finish the job, which is the remaining property. So here we defined f schlick, but we only know what it does for smooth maps. We don't know what it's doing for proper maps. So the fourth one, which I'll call D1 here. So this is where they will differ. For f proper, we want to prove that f schlick is isomorphic to f cross, the right adjoint. To R f lower star. And D2, the other issue that the similar issue that comes up here is that for f smooth, the remaining unfinished part here is that you want to prove that prove f schlick is isomorphic to f smooth, meaning it does what it's supposed to, what we expect to get for smooth maps. So this is how one tries to construct the theory. Both these theories involve a lot of technicalities, and now I'll very briefly mention some of these things. So, and some of these details are non-trivial. So let's start with the property C, the existence of factorizations. So property C2, which is on the other side, this is known to be true. It's a non-trivial theorem due to Nagata. And it's called the Nagata compactification theorem. So in our context, it says exactly what we are expecting, that any finite type map separated can be compactified. So it can be factored as an open immersion into a proper map. So this is Nagata compactification theorem. Yeah. Yeah, so third property for smooth maps, essentially your functor should have meaningful geometric properties. Otherwise, it's not probably going to be useful. So if you just, for example, just look for right adjoint, it's not clear what you have achieved. I mean, it is interesting, but what is that right adjoint doing? What does it give you? It's not clear. Whereas if you go back to Verdier duality, you would notice that f upper schlick of anything was giving you twisted by the orientation sheaf. So there is some, it is related to what the manifold look like. And here also we want something like that. If it is a smooth manifold, it should be related to what the geometric properties of the manifold. So of course, Serre duality already has this, but it has it for smooth projective or maybe smooth projective variety. So we are trying to extend it, but even if it is not projective, even if it is not proper, we want it to have this geometric property. It's otherwise it's I mean that functor may not be much useful in geometry. No, as I said, the right adjoint is not a localized, is not well behaved under localization. For open immersion, the right adjoint, it gives you something else. And so therefore, if you compute the right adjoint and restrict to an open set, you will not get something, something nicer. So it's not that interesting. So for example, if you take a smooth projective variety, and then the right adjoint has to look like this. But if you take a quasi-projective, take an open subset of that smooth projective variety, and then try to compute the right adjoint, it will not give you this. It will give you, meaning it will not give you f upper star tensored with this. It will give you something else, and that is not so interesting. And again, same reason that if I have an open immersion, the right adjoint is not restriction. So it'll give you something complicated. composed with this. So for smooth projective, you'll get this, but for the open set, you'll get some other functor, and composed with this, it'll completely mess it up. Meaning it'll give you something somewhat complicated. F is smooth at regular at a point. Or you mean what happens over the smooth locus? So yeah, so over the smooth locus, these conditions will guarantee that it will still look like this. Because the smooth locus, okay, let's pretend, to simplify things, let's pretend Y is a point. Then you're asking what happens on the smooth locus. Well, that's an open subset. And for open immersions, I'm requiring it to be this thing. And we will prove that for smooth, it'll follow from these, that for on the smooth locus, it will still look like this. That's one of the things that will come out of this. Okay, so C2 is known to be true. On the other hand, C1 is known to be false. So just to give us this thing, there exists complete variety over any field like complex numbers, if you like. So complete again means proper. Maybe I should just say proper variety. X, whose Picard group is, so let's say over K is equal to K bar, whose Picard group is known to be, whose Picard group is trivial, such that Picard group is trivial, zero group. And so one can show that such an X is not embeddable. Not embeddable in any smooth. Smooth variety. So there is one example due to Madhav Nori, but I think there are also toric examples in dimensions 3 and higher. So this means that we run into a problem here. We can't really factorize it. Of course, here we only took a factorization of this kind. You could probably jumble things up, and but still it's not clear whether you can sort of generate, you can write any map as a composites, finite composites of closed immersions and smooth maps. Such an X is not embeddable, meaning as a closed subset, closed subvariety in any smooth variety. Basically you have to, if you have a smooth variety which contains it, you have to look at a effective line bundle there and then say that it's restricted. You can choose an effective line bundle there whose restriction to X will also be effective. But Picard group is trivial, so you cannot have such an effective line bundle. That's the outline. But what we do have, and that is why that approach still survives, is that you have locally you can still get such factorizations. Such factorizations are known to exist, or such factorizations are easily found. I shouldn't say. And basically just go to an affine picture, and then I am just looking at that's your factorization. So locally, just polynomial ring, modulo, and ideal, because you are looking for a closed immersion into a smooth map. So locally, such things exist. So locally, such a factorization exists. So therefore, one has something and something to start with. And so this first approach uses this, but it gets into a lot of complications. So, so I won't say much except that the first approach, the constructive approach, starts off like this, but gets into many complications. And there will be a lot of restrictions also around about process. Okay, and the other remark is the questions A and B. So C and D will come later anyway. Sorry, the C I've already addressed. D can be done later, and A and B just involve checking a lot of diagrams. So it involves diagram chasing. Not all of it is straightforward, and so I will just mention one or two things which show up there because they are interesting and they are related to residues and duality. Or sorry, residues and trace maps. So I'll leave that for the time being, and I'll say something about those two approaches again later. So we will need some explicit calculations, which again, I won't go through all the details, but I'll just give a sketch. So some explicit calculations. So first is take the projective space over Y. Look at the natural map, ENY to Y. Then the claim is there exists an isomorphism you can see why this isomorphism might show up. Okay, so before that, let's place this map in that picture. This is both a smooth map and a proper map. So it's somewhere here. And you sort of expect both the properties. So you expect it to be given by that explicit formula, but you also expect, this picture is suggesting that it will have the right adjointness property. And so that tells you that if you apply RF, or in this case, I'm calling it pi, so R pi lower star, replace F by pi everywhere, then there should be a, so ignore this for the time being. You can assume that the input there was OY. So this is not contributing anything. So if you apply R pi lower star, essentially you are computing it over here. And that should give a map to O. So there exists an isomorphism, which were there denoted it by integral. So I will also denote it by integral. I mean, it's common practice. From Rn pi lower star of omega n pi, so relative module of differentials, OY. And thereby giving us a map of complexes. So this is kind of expected to result from the co-unit of adjunction, where the adjunction is really the adjunction to RF lower star applied to the fact that we also expect F shriek not only to be right adjoint to F lower star, but also to look like this, because P and Y is both proper and smooth. So our formulas are predicting that there should be an isomorphism like this. And this is all standard, at least locally. So that's what I'm going to say here. So thereby giving us a map of complexes. R pi lower star omega n pi shifted by n y. So this is like your f upper shriek of OY, and then or pi upper shriek of OY. This is R pi lower star pi upper shriek of OY to OY. And that's because pi upper shriek is also right adjoint. So this is based on some explicit calculations, which is done in standard textbooks in algebraic geometry. But so I will just very briefly sketch this and move on. You take an open set inside Y. So then locally, this is looking like this map, where this is proj of A 0 to Tn. And so with this, we can say that R pi lower star omega n pi. If you look at this module, R n pi, sorry. And if you compute this over the open set U, which is spec A, then this is, you can compute it using check cohomology. And so this is check cohomology over the sequence E, tensored, check, so this is the check complex. I'll be a little loose with subscripts over tensor, but it's just see it from the context. And that's isomorphic to again the same check complex. Okay, so instead of writing isomorph like this, let me just say that this is also, though non-canonically, isomorphic to OPN of minus n minus 1. That comes from the Euler sequence. So this is via Euler sequence. So there's an exact sequence for omega 1. I mean, there's an exact sequence which involves omega 1 as a syzygy. And if you use that, then you can prove this. And so then this will turn, then there's an explicit calculation which will show that this is isomorphic to A. And so anyway, I'm not going to do all the calculations, but this fact is in fact done in, for example, Hartshorne's textbook. You can find it there. And if you check it carefully, then these isomorphisms glue over various U's, etc. So that is a quick outline of how this is checked. A couple of things to be mentioned about this. One is that if you look at this isomorphism going from this module to this one A here, this is the A module A. So the element 1 corresponds to a particular element here. So the element in Rn pi lower star omega n pi corresponding to 1 in A is given by, okay, I shouldn't probably say, I mean, it's more like the check command. Never mind. Sorry. I'm just going to erase this. I want to think of it as a check fraction. So I want the next term here, which is this one. So sequence P, tensor to omega and I restricted to U is given by or given over the open set. So this is in the nth, so this is the nth check co-cycle. So therefore, you have to go to the n+1 fold cover intersection. So over the intersection, EI not equal to 0 by the fraction where we'll make the ad hoc choice of dehomogenizing with respect to the first variable. So where Ti is equal to Ei over T0. But in fact, that actually doesn't matter. So, and that's the key point. And in fact, this is actually a very important point in this whole business. It's chasing through this element, which makes a lot of things work. And the things I want to talk about, residues and traces, are also related to this kind of expression. So this element is independent is in fact independent of the choice of the coordinates. So you can check this by going to a suitable open set, affine open set here, and doing some explicit calculations. So you can check that this is in fact independent of. So here we chose this. So what I mean is that if you do say a linear change of linear transform, if you did a linear change of variables here, then and then compute this fraction, you'll get the same. You get the same number, a quantity. So it is in that sense, it's actually independent of the choice of coordinates. Yeah. Pardon? Is it because it is symmetric? No, yeah, well, basically what you have to check is that the way this fraction transforms under a linear change of variables, that will affect the way the denominator also changes. The denominator changes, meaning, see, actually there are signs involved in the denominator also, because you choose, when we do the check computation, we write down the variables in a particular order, and then we do the intersection of the open sets, and then we set up the boundary maps, etc. So what you can check is that, for example, if you multiply one of these TIs by a constant, that TI also gets multiplied here. So certainly multiplying one of the variables by a constant will get cancelled out. But then you have to also check if you permute two variables, what happens. You can check that that also cancels out. If you set up the signs correctly for the check cohomology computation, and here you'll see that that also gets cancelled out. So if you keep doing linear change of coordinates, things will get cancelled out. But in fact, it's, I mean, here I'm pretending I'm doing linear change of coordinates among little TIs, but in fact, you can do it over capital TIs also. So all that you have to do a bit of check. Is the mic on? Okay. And finally, if you look at the functor pi smooth, which is given by pi upper star tensored with omega n pi shifted by n. This is a right adjoint So this is not, again, completely obvious, needs a proof finally. So I'll just say one checks that. It's right adjoint to r pi lower star with co-unit of adjunction being yeah 2 1 being induced by the integration map there. So that this is setting it up the co-unit map only for one module, which is OI, but that is good enough, meaning it's induced by integral pi and what is called as a projection formula. Maybe I'll keep this. Yeah, I think I don't need this one. So projection formula will say that if you apply, r pi lower star to this, then that's the same as just this tensored with r pi lower star of this. And for this, I have the integration map, and or I will be just denoted by the integration symbol, and that map will send it to pi. In fact, this is an isomorphism, and so that will then give us a map like this. But that isomorphism is, sorry, never mind. So that isomorphism is only at the nth level. What I really have is a map of complexes like this. And so that will then give us this map for not just OY, but for any complex over Y, any, let's say, bounded below complex over Y. So this one checks. So this you can check over. Check. Maybe I'll just leave it as that statement. So this is, you can find a proof of this in, let's see. I mean, it's there in Hartshorne's, the other book, Residues and Duality, or EGA. But I think you can also use something given in Hartshorne's book, Hartshorne's textbook in algebraic geometry. You can use some methods like that also to prove it probably. So maybe I'll not say anything about it. I'll just leave it there. So that is one explicit calculation. The other explicit calculation, which is used in both the approaches in some sense, is the following. So you take a closed immersion. Locally given by a regular sequence of length n. So it's what is called as a regular immersion, but I just want to have that number n also. So locally given by a regular sequences of length n. So locally the ideal is given by a regular sequence, is generated by a regular sequence of length n. So take the ideal, let I OX be the ideal defining y in X. Then we already had a sort of an explicit formula for the right adjoint to lower star. And so let me remind you, we already knew that I cross is isomorphic. So the right adjoint to lower star can be explicitly calculated by looking at sections supported along y. So this is OX, sheaf R Hom dot. So this is always sheaf Hom. I hope I wrote sheaf Hom dot last time also. And then this is, sorry. So, okay, so let me modify, let me put a G here, not that it matters so much. Sorry about that. I'll put G here, G dot, G dot. And this is of course restricted to y. Now this is isomorphic to, you can see this is isomorphic to R Hom dot OX. Now OX mod I is a perfect complex over X. And so therefore you can actually put OX mod I here and OX here and tensor with G dot here. No, OX mod I is a perfect complex. G dot is just anything in DQC plus. Because it's locally given by regular sequence. So it's a perfect complex. And then this whole thing restricted to y. Now I'm going to interpret this one. So, but before that, let's do a quick side calculation somewhere. Maybe I'll do it here. And so I hope you can read this. I'll write it a little small. So this is Hom A. So first let me say locally. So locally, I will go to some suitably small open set where the ideal is actually given by a regular sequence of length n. And if that regular sequence is given by denoted by T, then I'll have Hom A, and then this is R Hom, but I'm going to replace it by Koszul resolution here. So I will put K lower dot of T, comma A. So I'm basically targeting this thing here, this expression. And this is of course isomorphic to Hom just K upper dot of T. This is the Koszul co-complex. But you can also say non-canonically, this is isomorphic to the, I said length n, so wedge n over A. So I'm being a bit loose here. I'm writing it everything over rings and over spec A. I'm just identifying quasi-coherent modules over spec A and the corresponding modules over the ring. I'll be a bit loose about that here. So this is going to be wedge R n T over E square whole dual. So this is again going to be so basically this is, okay, sorry, there should be an intermediate step here. Maybe you can say this is isomorphic to, I hope I can write here, A mod, what is it, the last Koszul homology, which is A mod T. And that's non-canonically isomorphic to this one. So till here it's some sort of canonical isomorphism. Here I chose a non-canonical one, but I won't say a non-canonical one, it's some strange one. Both of them are isomorphic to A mod T, but this one will be work better if you change the regular sequence. And so using that, what we get is that this is isomorphic to our wedge n I mod I square dual shifted by minus n, because it's, oh, there's an n here, sorry, n, and that is isomorphic to an n here. I hope you can read this. An n here. Sorry, minus n. N to the right, which by convention is minus n. And tensored with G dot. And the whole thing restricted to Y. But the point is that the reason for doing all this circus is that this, if you do it this way, then this isomorphism is independent of the choice of local that sequence. So this is canonical. So that's the whole point of doing this. And this is all, again, these ideas you can find in Hartshorne's algebraic geometry textbook also. And so then this is, you can just rewrite this as Li upper star G dot tensored with wedge n I mod I square dual shifted by minus n. So I got rid of the restriction to Y by putting that Li upper star G. Here everything was actually tensor over X, so I should be careful here. This was derived tensor over OX. Now I'll put, this is just tensor over OI. It's also derived tensor, but that I mod I square will be locally free. Wedge n I mod I square will be invertible module, so that will work out. So we have a very explicit formula now, and this is kind of crucial. This is also useful. So both these calculations are useful in the first approach as well as in the second approach to settle some certain aspects of the theory. And I will just maybe orally say something about that. So for example, if you want to follow up on the constructive approach, if you ignore, for the time being, ignore the problem arising from the fact that C1 doesn't hold, that you can't always factor things like this, but locally you can factor. So for example, you can concentrate on quasi-projective maps, or what are called as embeddable maps. I think that's the same as quasi-projective maps. So you can look at such maps and you can try to set up a theory of Schlick by using this formula. You will run into a bunch of compatibilities. But what one will show is that certainly every relative projective space has the right adjoint property, but also because closed immersions also you can write down the adjoint explicitly. You can see that so you can explicitly see what the right adjoint will look like for any quasi-projective map. You can write down very explicitly, because for projective space you have an explicit formula, and then that also works as H cross. H cross is isomorphic to H smooth, and then H cross and I cross put together will give you the right adjoint to lower star. Moreover, if X happens to be smooth over Y, and you factored it like this, then you can also see that for such a smooth map, for a proper smooth, then it will be projective smooth map over Y. And in that case also you can see that the upper Schlick functor is actually nothing but tensoring with omega. Because what you will get is, what will happen is that this will be given by regular sequence locally, and this is given by omega of this ambient projective space. So I'm pretending this is projective space and this is a closed subscheme, and this whole thing is a smooth map. So then this will be a regular embedding, and this will be projective space. You will have a module of differentials coming from here, and you will have this wedge I mod I square coming from here. you put them together, you can see that what you will get is the model of differentials, tensoring by model of differentials of this one. So any projective variety you can, or projective map, you can set up f upper Schrick for smooth projective map. You can see that f upper Schrick is just given by tensoring with model of differentials. You will also come across a lot of compatibilities. Many of them can be settled in an easy way, but the most interesting ones will be, which will require a little bit of handling with care, will be the situation where you factor the identity map as a closed immersion followed by a smooth map. So you can see that among various compatibilities that you'll need, that is one of the situations which arises. And again, that can be handled using 2, because if you factor the identity map as a closed immersion followed by smooth map, you can see that this is given by regular immersion. And again, you have explicit formulas for both sides. And so you can work out everything and you can prove whatever compatibility you're looking for. I'm not saying everything is easy or straightforward, but these calculations are somehow at the core of all the verifications that we have. That is if you take the constructive approach. And okay, this one maybe I'll talk a little later. So I'll complete the story on this side. What happens, the reason being that there are certain things which arise here which one cannot really ignore because they are interesting in their own right. And so how does this theory get completed if you cannot factor every map as a closed immersion into a smooth map? So that is the issue I will now next address. And we will see that residues and traces can arise naturally there also. So what we know is that we have local factorizations like this. So let's exploit that. So let's look at the class of maps for which you have such factorizations. Let's call them embeddable maps, or maybe we should just look at quasi-projective maps. So consider take essentially it's a K scheme, finite type, separated, and assume F is embeddable. Embeddable means you can write it as a closed subscheme of some smooth scheme. Example, quasi-projective. So that F Schrick can be constructed A1 and B1. So, I mean, even though we don't have a theory of Schrick for all possible maps, we still can use this formula and assume that A1 and B1, meaning all these compatibilities have been proved. They can be proved using these explicit calculations that I have here and some various other compatibilities which are slightly easier to handle. Then, and this was a key observation by Grothendieck. This was one of the interesting observations by Grothendieck. He mentions it in his ICM article where he announced a solution to the duality problem, generalizing the duality theorem to arbitrary maps. So F upper Schrick K is isomorphic in the derived category. So in dx to a bounded complex, which we'll call a residual complex. And I will very briefly say what it looks like. Of injectives with coherent homology. Coherent means it's quasi-coherent and it's finitely generated. I mean, this should suffice for us in this context. So locally over affine patches, it's given by finitely generated modules. The homology will be coherent. Of course, these injectives tend to be rather big, so they will almost never be coherent. Sorry, this is not a full stop here, which has the following form. Having the following form. What's it going to look like? So first of all, just to summarize, we are saying that there will be a quasi-isomorphism to another complex. I hope that's what I've written here. Yeah, it's isomorphic in dx, low bounded residual complex. So in fact, I think there's an explicit map, or I think I've forgotten now. Is there a on the nose map or just a derived category map? That's what I'll say. That's the residual complex. So here dimension x is n. And so what does EF apostolic look like? So it's going to look like a complex direct sum E kappa of P, and in fact every term will look like this only, except the direct sum will vary. Sorry? Oh yeah, you're saying you can represent it by, of course, yeah. Yes. Now what I meant was, yeah, I should be knowing this because I've worked on this, but now I forgot. So there is for a single module, I know you can give a map and okay. Anyway, it doesn't matter. So there you can write down, and I mean, there will always, as Srikanth pointed out, there will always exist a natural map like this because it consists of injectives. So let me complete the story here, or sentence here. So here, every term looks like this, but they are over different points. So here, transcendence degree of kappa of P over K is 0. So these are like the closed points, and these are like the generic points. So here, I'm direct sum over transcendence degree of kappa P over K is n. And n is a dimension of x. So this is, maybe I should use color chalk. So this is in 0th spot. And this is in minus nth spot. So it's a bounded complex of length n. And this is what it looks like. So these are various injective hulls of various points. And those points are indexed by the codimension. I mean the transcendence of that point, the residue field over the field K you started with. So where, again, just to write it out, E of kappa P is equal to envelope injective, whatever, call it envelope or injective hull of kappa residue field kappa P. So here, of course, P belongs to X. I mean, that's P belongs to X, but over the local ring OXP. So it's various injective hulls. Of course, you have to also put a tilde maybe. We will look at the quasi-coherent sheaf generated by them. So those will be sort of like skyscraper sheaves based on different points. And this, you can say where this is coming from. This is actually explicitly given by so details you can find in Hartshorne's Residues and Duality. So resulting from the filtration, we put upper indices. Empty set where Zi is equal to all those P in X, such that transcendence degree of K of P, kappa of P over K is, okay, so these are decreasing, so you can work it out what it should, n minus n. So when I is n, you're here, and it's those which are less than or equal to 0. So those are the closed points. N plus 1 is empty, and when n is 0, those are the generic. I is 0, it's like the generic points, or the highest codimension points. And so this filtration is giving rise to this sequence via the following process. And so what you do is you look at of whatever. You can feed in anything you like here. So I'm putting f of k here, and then it ends with hn zn over zn plus 1 f of k goes to 0. And you can see where the boundary maps are coming by. They are coming by certain what do you call them? The connecting homomorphisms associated to. So you can write down gamma, Z0, gamma sections with support in Z0, with support in Z1, etc. You have this decreasing family of subfunctors, and then you can write down certain short exact sequences involving consecutive ones, and then you get certain long exact sequences, and they will have connecting homomorphisms. Connecting homomorphisms of those long exact sequences give rise to this. And what you can see is that each one of these is actually going to be living on a certain skeleton. So this will be consisting, this will basically be consisting of only points where the codimension is exactly 0. I mean, the transcendence degree is exactly n, and so on and so forth. So here the transcendence, these will be corresponding to points whose transcendence degree is exactly 0. And so it will, what one can prove, this needs some proof. I'm not going to go over the proof. So, oh, time is up. All right, so maybe whatever else I wanted to say, I will say, just say it orally and I stop here. I want to give one example, but I think I don't have time. So just 2 minutes, I will say something. So this specific form is kind of useful because it gives you what is called as an auto duality, matrix-like duality for not just, so matrix duality, you will work with one injective hull and you will work with finite length modules over that local ring or yeah, finite length modules over that local ring if you want to get double duality. So here you can work with, if you put all of these put together over all the points, then you will get a duality which will work for any complex with coherent homology of any length, so even possibly infinite length. So any complex with coherent homology, you can double dualize with respect to this, and you'll get back what you started. So that auto duality is true for this kind of complex. So such a complex is called a dualizing complex, or actually we have this specific, I mean, f upper shriek is K is usually called dualizing complex, but this particular form of f upper shriek is called a residual complex. And what you can do is you can glue these complexes explicitly. So even though you don't have you don't have a theory of f upper shriek for arbitrary maps, you can construct them locally. Locally, the only thing you can glue is these residual complexes. Not arbitrary complexes you can't glue because in the derived category, gluing does not hold. But these complexes have such an explicit form that you can, in some sense, intuitively, you can imagine that you can actually glue them once you have the right conditions. You can glue them. And the key property is that I'll just write down one statement here, which is that if you take a dualizing complex here, let's call it k dot y, then as I said, you can glue dualizing complexes over various open sets, glue quote unquote given suitable data, and you can define f of h ky irrespective of whether you can factor this map like this or not. You can always define it. And so we'll call this as kx. So you can, given a residual complex here, you can define a residual. If y admits a residual complex, it's not clear it admits, but for all finite type field varieties over or schemes over k, it exists from what I've said there. So in general, if there exists such a complex, you can find an f of h of that, and that will be a complex which has which will also be residual. And the key property which is used, which works here, is the following statement, which says that f of h of any complex g dot on y is isomorphic to, so you dualize g dot on y with respect to k dot y, pull it back, and then dualize it again. So dualize g dot on y using k dot y, pull it back, just pull it back f of a star, and then dualize it again. It will turn out that this is isomorphic to f of h g, provided g dot has coherent homology. Because you're doing this dualizing business, you always need a coherence hypothesis. So this bootstrapping process allows you to define f of h in the first approach. This is where I'll stop here.
So are there any questions?
Yeah. Yeah. So initially I made the assumption that maybe it's quasi-projective or something, and I can define f of h, right? So then I can get this complex. So over quasi-projective varieties, I have plenty of, I have this residual complex. What I'm saying is that if I had a proper variety, I cover it by quasi-projective varieties, and each one of them I look at f of h k given by this, then I claim that I can glue them because of this specific form. It requires work. I'm not saying it's trivial. If it exists, it may or may not exist. No, I have said that I can get a residual complex when it is embeddable and when I can, when I have an f of h and then I look at f of h k and I do this e f of h k, I'll get a residual complex. Sure, but I need this f of h to begin with. No, I have not given any formula because I need f of h k. How do I write this without knowing what is f of h? No, you need this map, you need this inject, that is just the graded underlying graded object. How do you define the differential, these differentials? No. Yeah, it involves f of h k. You need, it's coming from this process. No, as I said, it's the connecting homomorphisms of, you write down 3 of them and then you'll get an exact sequence. Or write down 2 of them. You'll get gamma z1 sitting inside gamma z0, and the quotient will be gamma z1 over z0. You can call it like that. Write down a long exact sequence of cohomology, and then look at the connecting homomorphisms. Then do it for every pair, successive pair, and you'll get some maps like this. So it requires. It'll have coherent homology. Yes, it'll have the property that it has, that needs to be checked. You can check it locally by first looking for smooth maps and then checking for closed immersions. You just check them for separately, that it will have this coherent homology property, and then you can get that. Yes. I mean, these are not closed subsets. These are specialization closed subsets. Yeah, it is. But I think, where is Gersten something, Gersten theory, yeah. It's similar, yeah. So Gersten, this in K theory, or not K theory, whatever, this quadratic something. Okay, K theory, okay, whatever, something. There some similar sequence arises. So I don't know what specialization, but this particular form of coming up thing, then filtration, start with the filtration and then write down some sequences, something like this. Yeah. Yeah. Yes. Not necessarily compatible with maps in the sense. Yeah. You can construct using this process over these open sets. What is X and Y? Where did now? Oh, two different. Okay. Yes. Yeah, I mean, yeah, it will be. No, it's not a given. You have to prove. I mean, yeah. I mean, that was my thesis or whatever. I mean, it's part of my, not my thesis, but sort of. Yes. If you know some things about them, you can, I mean, that's why you can glue them also. I mean, you can, yeah. The thing is, you have to keep in mind that we are not looking at arbitrary residual complexes. We are looking at the one coming from this particular process. So this already has certain properties built into it. F shriek, G shriek is isomorphic to GF shriek and all those things. So those properties will translate into gluing data for you if you have an open cover and then you have restriction maps. Then you already have some data coming from here. That will translate into gluing data for the residual complex. And if you have a map from X to Y, it will allow you to transport a residual complex from Y to a residual complex. Yeah, it needs a proof. But it's there in Hartshorne, but he only sketches it. And Conrad sort of mentions that, yeah, it's okay. Yeah. Any other questions?
Any further questions?
We should ask.
Okay, so let's thank the speaker.